Hi, my name is Akshara Srinivas and I'm from Srinivas, Washington. Today, I'd like to introduce you to my research, Albatross. Over millions of years, the albatross has found a way to fly for kilometers together without even having to flap its wings. And it does this by treating the wind as a source of energy rather than a disturbance. Modern-day UAVs end up doing the exact opposite. They fight against turbulence in the wind, which means that they lose out on the energy available in the atmosphere. My question was simple. Can I teach a UAV to fly like an albatross? And the short answer is yes. Let me show you how. The first type of turbulence is orographic wind, which is where the albatross gets lifted up like a parachute. The second one is wind gusts, and that's when the albatross is getting tossed up and down, but it takes control of the wind again, and it uses it to lift itself up or dive down with the turbulence. And the third one is the wind shear, where the albatross performs the Rayleigh cycle, which is a net zero energy loop, and it can perform this for days on end without even having to flap its wings. So now we've discussed how the albatross soars, but now we also have to talk about UAVs. There are three existing modes for UAVs. The first one is the speed hold maneuver, and this is essentially when the UAV is traveling and it can get moved up and down, side to side by a turbulence, but as long as it's keeping the same velocity throughout, the UAV will just ignore the turbulence entirely. It has one mission, and that's to maintain its speed. The other mode is also similar, but instead of maintaining speed, it's working on maintaining altitude. So let's say the altitude mode gets hit up by a gust or orographic wind, it'll turn its throttle up and actively fight that gust in order to get back to the same altitude it was already traveling at. This means that it ends up using more energy to fight against the turbulence, but it's really stable, which is good for things like surveillance, which is what UAVs are commonly used for. Now, since both of these modes end up ignoring or fighting against turbulence, that makes them extremely inefficient. So a few years ago, scientists realized that there was room in the field of UAVs to work on efficiency and how to make sure that UAVs can have sustained flight. That's when scientists invented the total energy control system, which I like to refer to as the energy mode. Energy mode is trying to maintain its specific energy, which means that it basically recognizes when the wind is helping it out, and in that point, it'll turn off its throttle. At this point, I realized that there was a lot of energy left out on the table in the form of crosswinds and downward gusts. So I went back to the Albatross to study its flight mechanics further, and that's how it developed the Albatross autopilot system, which I get to present to you today. The Albatross does a few seemingly small maneuvers that end up having a really large impact in the results. Let me walk you through those. The first one comes with orographic wind and upward gusts. When the albatross hits these, it performs a pitch maneuver where it turns itself perpendicular to the orographic wind, so that it's maximizing the lift that it gets out of the turbulence and therefore maximizing the energy that it retrieves. The second one is downward gusts, and the albatross treats it in the same way that the actual bird does. It treats it like a tailwind and dives down with the gust to increase its kinetic energy, which also increases its overall specific energy. Now, performing all these maneuvers at random times can actually be counterproductive. So when I was studying the albatross's flight mechanics, I understood that it synchronizes its maneuvers to its natural frequency. Let me explain. Imagine that you're pushing a swing. When you're pushing the swing, would you rather push it on its way down or its way up? Probably on its way down. That's because when you're pushing the swing on its way down, you're getting the most out of the energy that you're putting into the swing. Essentially, you're coordinating your maneuver of pushing the swing with the swing's natural oscillation. When the gust hits a UAV, it starts to wobble around its center of moment, and that's what the oscillation is. Now, the frequency of these oscillations is dependent on the UAV itself and its weight loading, but the amplitude can change based off the turbulence. So when the albatross mode encounters this kind of turbulence through gusts or whatever it may be, it starts to measure the frequency of its oscillations. And then it uses its elevator to maintain that same frequency at an extremely low amplitude. This way, the next time the albatross encounters a gust or any type of turbulence, it can make sure it's matching its maneuver to its natural frequency. And this way, the albatross is never working against its own natural oscillations or the turbulence in the atmosphere, making each maneuver that the albatross makes a positive energy loop. I took these core principles and I converted them into 10 mathematical equations, which are able to accurately represent the albatross bird's exact flight mechanics. Now let's take a look at the hardware I built for my autopilot software. All of this starts with the PixHawk, and the PixHawk has three main sensors that I used here. The first one is the GPS sensor, which tells me the X and Y coordinates of the plane at any given time. The next one is the IMU sensor, which tells me the X, Y, and Z acceleration of the plane. And then the third one is the barometer, which tells me the altitude of the plane and therefore its Z direction. The PixHawk records all of this information and it sends it through this telemetry air module. The telemetry air module is connected to the telemetry ground module, which is over here, and that's what's sending the information into my computer for the code to receive and then process. Then it gets the outputs in the form of coordinated pitch and roll maneuvers for the UAV to complete. And it sends these back through the ground module, to the air module, and to the PixHawk. And the PixHawk sends it through these servo cables to each of the control surfaces on my UAV. This happens 20 times each second. I codified these 10 equations into a control loop, capable of autopiloting a UAV in both a simulated and real-world environment. As I mentioned earlier, I started by creating a physics-aware reactive control system, which was capable of flying a plane in the simulated autopilot environment. This allowed me to have fine-grained control of environmental and aerodynamic constraints, such as turbulence and aspect ratio. I took a series of 360 tests in total, with 9 different turbulence settings, 4 different control modes, and 10 tests of each. I used 2 experimental setups to test my Albatross autopilot module. For the first one, I created a software-in-the-loop system, while on the second one, I built an actual plane which I flew in open air. For my physical test, over 80 real-world flights, I found that the Albatross had a 23% gain in efficiency over the existing energy mode, with a p-value of 0.001 and a Cohen's d-value of 2.7, proving statistical significance. In my simulated experiments, I was able to have more fine-grained control over the different turbulence settings, and I found that the Albatross's performance was peaking at levels of 0.5 to 1.5 in the turbulence, which matches around the same turbulence intensity as Earth's environment. And this tells me a few really interesting things. The first one is that my Albatross control system has turned out to be extremely good in Earth's environment, which is great because it's adapted to match the environment it's going to be flying in. But along with that, since the Albatross over millions of years has been able to adapt to perform best in Earth's actual environment, and my control system does the same, it tells me that I was able to accurately mathematically represent the exact flight mechanics of an Albatross in a UAV's control system, except I did it in a few months rather than a few millions of years. Along with this in my flights, I found that the Albatross was performing a lot more of these coordinated roll maneuvers, much more than the other 3 control systems did. If you look at the graph, you'll see that the roll maneuvers the Albatross were performing were in fact almost chaotic, and they were very drastic. This shows how the Albatross traded stability for efficiency. This MIT paper mathematically proves that net zero energy flight is actually possible, which means that as I do more iterations of Albatross, I'm only going to get closer to that goal. My plan for the next iteration is to play around with the idea of thermals. Thermals are another type of turbulence, and they're caused by random spots on the Earth where the Earth is actually hotter than normal. And since hot air rises, a lot of soaring birds will actually hover around these thermals and just circle around them as they gain altitude and potential energy. I want to see if I can incorporate that into my Albatross software. With the Albatross mode, the next generation of UAVs won't just survive in turbulent wind. They'll learn to thrive in it. Thank you for considering my application.